Picture this. You're spinning a raw, heavy block of solid steel at literally thousands of revolutions per minute. And then you forcefully drive a stationary tungsten carbide blade right into it. Yeah, it's intense. That is the violent, extreme physical environment of a CNC lathe. We're talking about the high-stakes world of subtractive manufacturing here, and it is absolutely amazing to see where immense physics, extreme heat, and incredible cutting forces all collide.
But what happens if that machine is fed the wrong material? Well, the consequences are pretty severe. We're looking at catastrophic tool failure or complete dimensional instability. We're talking ruined parts, shattered blades, or even lethal hazards like bird nesting. That's when those sharp, continuous metal chips wrap violently around the spinning chuck. Honestly, in this environment, the margin for error is essentially zero.
So, welcome to this explainer on CNC lathe material selection, the physics of turning. Together, we're going to completely demystify this highly calculated dance of chemistry, physics, and economics that dictates literally every single cut on a CNC turning center. It's an incredible balancing act, and really understanding it is the absolute key to mastering modern manufacturing.
Okay, let's dive into this. Here is our roadmap for today. 1. Inside the lathe. 2. The material master list. 3. Trade-offs and tactics. And finally, 4. Real-world applications.
Starting off with Section 1, Inside the Lathe. Let's look at the actual physics of machining.
So, before we even introduce our cast of specific metals, we really need to look at the invisible forces at play here. Machinability? It isn't just one simple metric. It's a complex puzzle governed by 3 major physical forces. First up is chip formation. The ultimate goal is producing clean C-shaped or C-shaped chips that just easily fall away. You absolutely want to avoid those continuous, stringy chips that wrap around the chuck and create that super hazardous bird nesting effect we just talked about. Then we have thermal conductivity, which is all about heat management, and finally, work hardening.
Let's look a little closer at work hardening. This is this wild phenomenon where material actually becomes harder and more brittle as it gets deformed by the cutting tool. So if your feed rate is too shallow, the tool kind of just rubs against the metal instead of cleanly slicing it. And doing that creates a hardened surface layer that acts like a literal suit of armor. Actually, it's so tough, it can completely destroy your cutting tool on the very next pass.
And this brings us right to thermal conductivity. See, aluminum has high thermal conductivity, so all that intense heat safely moves right out into the chips and the workpiece. Titanium, on the other hand, it has incredibly low thermal conductivity. The heat literally has nowhere to go, so it just gets trapped right at the cutting edge. That is exactly why machining titanium demands some really advanced physical and chemical vapor deposition coatings, your PVDs or CVDs, just to survive that localized inferno.
Moving on to Section 2, the material master list. Let's talk about the different classes of materials.
We can actually look at these materials almost like distinct personalities. They each have their own little quirks and temperaments on the lathe. Broadly speaking, we divide workpieces into 3 classes. You got your non-ferrous metals like aluminum 6061 and brass C360, which are prized for their strength-to-weight ratios and those incredibly fast, beautiful finishes. Then you have your ferrous, iron-based heavy hitters, think stainless 316L, known for extreme chemical resistance. And finally, engineering plastics like POM, which bring their own distinct solutions, like dimensional stability to the table.
Now, what's really interesting about this is the sheer variance in how these materials behave. You move from the highly cooperative, friendly brass C360 with a perfect benchmark score of 100 down to aluminum at 90, and then you just completely plummet to titanium grade 5 at a mere 30. That steep drop, that represents a massive increase in difficulty, tooling costs, and overall machining time.
But hey, even within the exact same difficulty tier, materials can frustrate machinists for entirely different metallurgical reasons. Take 1018 carbon steel and pure copper. 1018 steel is notoriously gummy. It's super prone to creating a built-up edge on the tool, which means you absolutely need high-pressure coolant. Pure copper, however, it's a total nightmare because of its extreme ductility and its heat-sinking properties. It tends to just tear and leave this awful, ragged surface behind, no matter how razor-sharp your cutting tool is.
And we definitely can't forget the engineering plastics. Now, these aren't your everyday household plastics. POM, also known as Delrin, is stiff with low friction, so it makes really consistent, manageable chips. PEEK is this high-performance polymer built for extreme high-temperature environments, but man, it requires incredibly precise heat management.
And then there's PTFE, or Teflon. It's incredibly chemically inert, sure, but it is so soft that operators have to be extremely careful just chucking it into the machine. I mean, they literally risk crushing the part before it's even cut. No way around it. You have to be gentle.
Okay, Section 3, Trade-offs and Tactics. How we actually adjust for these materials.
So, how does CNC programmers and machinists actually handle these diverse, stubborn materials? Well, it all starts with speed. Specifically, surface feet per minute, or SFM, which is the speed the material moves past the tool. Soft aluminum, you can turn that screaming fast. We're talking over 1,000 SFM. But hard titanium, you are severely restricted to around 150 SFM. If you choose the wrong speed for your material, for sure you are going to cause premature tool cratering or thermal cracking of your insert.
So, the crucial point here is that your tooling geometry absolutely must perfectly match your material's hardness. Hard materials demand a strong, honed, or T-land edge preparation just to survive all that immense pressure. Conversely, softer, more ductile materials, they require a dead sharp edge with a high positive rake angle. They basically need a razor to cleanly slice right through the material without just smearing it across the surface.
And then we have our coolant strategies, which are just as vital for lubrication and temperature control. Just look at 316 stainless steel. Hitting it with through-spindle, high-pressure coolant is often the absolute only way to keep the tool from overheating. But compare that to cast iron. Surprisingly, cast iron is often turned completely dry. Why? Well, because the graphite naturally found inside the iron actually acts as a built-in lubricant. If you added coolant, you just create this highly abrasive paste that would completely ruin the cutting process. Crazy, right?
Let's move to Section 4 and see how this all builds into real-world applications, looking at industry-specific needs.
See, all of these micro decisions on the lathe map directly to things we rely on every single day. Different industries prioritize completely different operational characteristics based on where that finished component is going to live. Aerospace needs supreme strength-to-weight ratios to reduce fuel consumption on planes, so they lean heavily on 7075 T6 aluminum and titanium. The medical industry needs non-reactive properties for human implants, so they use 316L stainless and titanium grade 5. Automotive focuses on 12L14 and 1045 steel for high-volume surface-hardened drivetrains, while the electronics sector needs the high conductivity and super-precise tolerances of C360 brass and tellurium copper.
But here's the catch. Even when you match the perfect material to the industry, the physics of machining can still completely trick you. Take thermal expansion in plastics, for example. A POM part can expand quite a bit just from the friction of being cut. If an operator measures that part while it's still warm on the machine, it might look absolutely perfect. But once it cools down to room temperature sitting on the client's desk, it shrinks. It becomes undersized and, unfortunately, completely useless. It's a real trap. Which brings us to our summary. Selecting the appropriate CNC lathe material is basically the ultimate engineering balancing act. You are constantly weighing the physical, functional requirements of the final part against the economic cost and the hard realities of machining performance. A truly skilled manufacturing engineer understands exactly how these distinct metals and plastics are going to react to heat, pressure, and cutting forces. It's this fascinating, high-stakes puzzle of chemistry and physics every single time a machine powers on. So, I'll leave you with this. If you had to balance function versus cost to actually machine your own high-performance part today, which material from our master list would you choose? Thank you so much for joining me on this explainer, and keep exploring the incredible world of material science.